for the kind invitation to come talk to you all today from as yet still dark Chicago, Illinois, and the US. I'm super excited to talk about this. I do encourage you to jump in and stop me at any time, since it can be a little lonely presenting from the privacy of your own home by your computer. So feel free to jump in for any reason. I want to acknowledge my collaborators. This work's funded by an NIH grant, which is PI'd by my coworker, Layla Parast, who's also at RAND. And then, like, as Boris said, some of this is work with him. And it's useful. Many of you probably don't know much about the RAND Corporation where I work. This is the building in Santa Monica, California, which is right next to the ocean and super fun to visit. And RAND is, a lot of people in the US don't know what RAND is, but RAND is just a nonprofit research organization focusing on public policy, or what people often call think tanks. And my job at RAND is similar to biostatistics job in most biostat departments or medical schools, where I just basically have a 100% research soft money gig. And people at RAND focus on a lot of things. There's a big portion of research at RAND that is focused on, like, national security and the Army, which I'm not involved in at all, but mostly I work in health and biostatistics and stuff like that. But so I'm going to start out just giving a pretty general overview of surrogate markers and why people might be interested in them, and then I'll jump into more of the meat of the longitudinal aspect. So surrogate markers are things you might be interested in if you have a gold standard outcome or a desired outcome that's too costly to collect in a future study. And for the purposes of this, I'll call the desired outcome Y and the surrogate S. And too costly to collect could mean a lot of different things. It could be that it takes too long to measure it. It could be that it's too difficult or too expensive, or some combination of all of the above. So here's just a sort of silly schematic of what that might look like. And so here's the desired outcome, which say it takes 10 months to measure whether the people in your study get COVID, but you'd like to be able to use immune response shortly after vaccination instead. Or the desired outcome might be something like disease status as determined by a detailed chart review by a physician, but the surrogate could be something that's routinely available in an electronic health record. So it could be all sorts of different things, but you just have some easier to measure surrogate that you'd like to use in place of some other outcome. And so when you're confronted with the possibility of using a surrogate instead of a gold standard outcome, the basic question that I think you should be interested in is the surrogate sufficiently like the gold standard outcome to be able to estimate the things that you want to estimate? And sort of more to the point, for what we'll actually be measuring here is that, can some function of the surrogate explain the effect that you're interested in? And so to formalize that notion a little bit, I'll introduce some notation. So for the purposes of this, we'll suppose that there's a treatment or an intervention or some other effect that you're interested in that takes two levels. So we'll call that thing A equals 1. And just for the purposes of the talk, it's useful to think about these two groups that you're trying to compare as treated and controlled, though there could be lots of different things. It doesn't need to be like a drug or something that you're looking at. And so then we'll introduce this notation, which indicates the counterfactual or potential outcome that you would observe if you were able to give this person treatment A equals little a. And similarly for the surrogates, we have the counterfactual outcome that you would observe if you're able to give them that particular treatment. And we don't actually get to observe the counterfactuals. We only get to observe each individual in the study under one of the treatment scenarios, but those counterfactuals, which we might not get to observe, are related to the observed data by this sort of standard function, which says that if you get A equals 1, then we observe your counterfactual under treatment equals 1. And if you get A equals 0, then we observe the other one. So then the effect of interest is just the difference between the expected difference between those two counterfactuals. And we'll call this thing the overall treatment effect. And so this, again, in the context of a vaccine study, would be the vaccine effect, what the expected outcome would be if you vaccinated everyone versus what the expected outcome would be if you didn't vaccinate anyone. So then the other sort of key quantity here is what we call the residual treatment effect. And that measures how much of the treatment effect goes away once you control for the surrogate. And this is a really similar quantity, which is the difference between the expectation of the outcome under treatment and the outcome under control, but now we control for the surrogates. And notice in this equation that the surrogate under treatment is takes the same value as the surrogate under control, and then we just integrate over some distribution. And the distribution that we integrate over is the distribution of the surrogates under control. And so what that means is this is the way you can interpret it is that this is the hypothetical treatment effect. If the distribution of the surrogates under treatment were forced to be the same as the distribution of the surrogates under control. So we see what the treatment effect would be if we were able to force the surrogates not to change, basically. Another way to think of it is the leftover treatment effect after accounting for the treatment effect on the surrogates. So then based on those two quantities, which again are defined based on these counterfactuals, so nothing so far is about the observed data, we can define the proportion of treatment effect explained by the surrogate. And we call this thing R, and it's just in the numerator, the difference between those two treatment effects, and denominator, the overall treatment effect. And this has been proposed by a bunch of people in the past. And it has the nice interpretation that if the surrogates are independent of the outcomes, then the numerator is equal to 0 because the two treatment effects are the same, and you get a proportion, a PTE of 0. And if all the treatment effect goes through the surrogate, then you get the residual treatment effect is 0, and you get a proportion of the treatment effect explained of 1. So this is it has a lot of intuitive appeal, and it sort of gives you a sense of whether your surrogate is able to account for the treatment effect that you want to measure. So a lot of methods exist to assess this PTE when S is a single marker, including a fully non-parametric method that my colleague Layla developed in 2016. And so again, here's this like sort of simple schematic where the outcome is measured, say, at 10 months, and the surrogate is measured at 5 months for everyone. But fewer methods are available when S is measured over time or measured longitudinally. And so now, instead of having S be measured just at a single time point, it actually captures the disease progression for each individual over a sequence of time points. People have actually looked at this quite a bit, but all the previous approaches have been model-based. So a lot of development has been in the joint modeling framework, where the outcome is a time to event, and the surrogate is a longitudinal marker, and then people have fit joint models for those two things. And a lot of other methods have used meta-analyses of multiple studies. And we're not working in either of those settings. We're working in a situation where you just have one study, and the outcome is not time to event. And we'd like to approach this in as non-parametric way as possible. So we'd like to make it not model-based if we can. And so that's where this paper that Layla and I wrote this past year comes in, which we call evaluating longitudinal surrogate markers, and it's in biometrics. So the outline for this portion of the talk is that I'll talk a little bit more about assumptions and preliminaries to set things up, and then I'll spend the most of the time talking about doing estimation, and then I'll talk a little bit about asymptotics and inference, and then I'll leave a little bit of time at the end for extensions into high dimensions. Are there any questions before I jump in? Cool. Okay, so a few more assumptions and preliminaries. In addition to the consistency assumption, which I showed you a little bit ago, which links the observed data to the counterfactual data, we also assume the sort of standard assumptions for causal inference, including the stable unit treatment value assumption, which means there's no interference between observations. And we assume randomization. So we assume that the treatment is basically completely randomized and independent of these counterfactuals. There are a bunch of technical assumptions in the paper. I'll mention a couple. The first is that the surrogate, which is longitudinal and measured over time, is a p-dimensional realization of a real valued function. So what that basically means is that for each individual, we observe them at p time points, and these p time points are the same for each individual. And that's in a lot of studies, that's going to be a pretty restrictive assumption. And we talk in the paper about how to approach the setting when you only have a few time points for each individual, and they might be at different time points. But I won't talk about that much today, but we can get back to it if you'd like. And then we assume that the counterfactual surrogates have the same support, which is again a sort of a typical assumption in causal inference. Okay, and so then the implications of those assumptions are that we can start to go from the definition of the PTE in terms of the counterfactuals to functions of the observed data, which we can then estimate. Because of randomization, we can estimate the overall treatment effect with just a simple difference in means. So we can just take the mean of the outcome in the treated group and the mean of the outcome of the control group and take their difference, and that gives us an estimate of the overall treatment effect. And then the residual treatment effect also, it turns out, depends on the mean and this sort of simple mean in the control group, but then it has this slightly more involved functional here. And basically that is the difficult part. This piece which links this piece which links this mean function, which involves the treated group, and this integration over the distribution of the control group is sort of the central difficulty of our approach. And so this is just rewriting everything, and you can see that everything just depends on the observed values of the yi's, except for this piece, which is this mean function. And you can think of that as just the association between the surrogate and the outcome and the treatment group. And so all we need to do is be able to estimate this regression function, basically, of y on s in the treatment group. And if we can do that, then we're done. We just plug it in and you have your estimator.
Excuse me, Denis, Cécile speaking. Will you explain how you deal with the repeated S measures? Because it's not clear to me where it appears on your slide.
Yeah, so this function is a function of all the repeated measures. It'll become clearer in a second when we start talking in more detail about estimation, I think.
Great, thank you.
Okay, so then how do you estimate that one key quantity, which is the relationship between the outcome and the surrogate? So we use a two-step process, which the first step is dimension reduction and the second step is kernel smoothing, and this allows us to be essentially as non-parametric as possible. But I think that a relevant question that you might have is, why not just directly estimate this regression function? We know how to specify regression models. So it's not immediately clear why you would want to do this two-step approach. The reason why we take this two-step approach is because it's just really difficult to specify regression models correctly, especially in this space. And like I said, we want to be as flexible and non-parametric as we possibly can. And kernel smoothing is what, like I said earlier, Layla has used in the past to evaluate a single surrogate marker. And kernel smoothing is a super powerful non-parametric regression method, which has lots of nice properties, but because of the cursive dimensionality, we can't just directly use it on S, because remember, this is a p-dimensional random variable. So directly using kernel smoothing won't work. So our proposal is to reduce the dimension of S using modern functional regression methods, using sort of like the unique features of longitudinal data. And that'll enable us to use kernel smoothing in a pretty effective way. So I want to give you a little bit of intuition about why this might work. And so if you take a simple example, I think it might start to build some of that intuition. So suppose that the mean function, suppose we just have 2 time points. This is, of course, a much sort of too simple of a scenario for what we're actually interested in, but it'll hopefully bring out some relevant ideas. So suppose this mean function that we want to estimate is just the sum of the squares of the 2 time points. And this just shows you the R code for doing a simple simulation that I'll show you. We can pretty badly misspecify that mean function and still recover a pretty good estimate of the mean by using this 2-stage approach. So suppose instead of having that true quadratic form, we just specify a simple linear model. So if we were specifying the correct model, both of these things would be squared, but we're just putting in linear terms. And you can see that the predicted values, which I have on the x-axis, are not super close to the true values. So if this m hat was a good predictor of m, then most of these dots would lie on the red line. But you can see, because we've misspecified the model, we don't pick up all of this curvature. And so it ends up being really far away in the tails of the distribution. And even here in the meat of the distribution, most of the dots are not, they're falling below this red line. But as you can sort of see from the picture, once we've done this initial model, it gives us a dimension in which we can actually start to find the true mean function, so that we're now in a single dimension, and this single dimension has captured enough of that relationship for us to be able to sort of use kernel smoothing, use a fully non-parametric approach to capture the relationship of interest. And so when we do that, this is now a smooth version of the original predicted values. We get something that's much closer to that red dotted line. So that's the basic idea of why we do this 2-stage approach and why we think it will work. And so we propose sort of 2 major ways to do this 2-stage estimation. The first 2 ways rely on functional models, functional regression models. And then the third way is uses the topology of functional spaces to sort of change the kernel space and make it possible to do smoothing. So to give you a sense of the regression approaches, the functional linear model looks like this. So now this mean function that we want to estimate, we specify it to be linear in the surrogates at the different time points. And then each one of the time points is multiplied by a beta, and both of the surrogate and the beta are coming from some smooth functions, we assume. And so you can estimate this smooth coefficient function using just penalized linear regression, essentially. The penalty term on the betas sort of manages how smooth the this function is allowed to be. And this is a really well-studied model, this functional linear model, and people understand it quite well. But you may feel like assuming this linearity is too restrictive of an assumption. And so you can also use an additive model, which is the same type of a generalization as the generalized additive models are in non-functional regression. But so instead of having everything be linear in the surrogate markers, over time, now we have some smooth function of both the surrogate and the time that we can estimate. And typically what's done is the basis expansion is used to approximate this smooth function, and then a penalty term is applied to control how smooth it's allowed to be. So the flavor of this model after the basis expansion is very similar to the previous functional linear model. And these models, it turns out, are pretty easy to fit. There is a relatively well-maintained package called Refund that has a suite of functional regression methods that you can use. And it's all built on top of MGCV. So then once you get those initial estimates of the regression function from those models, then we just plug that thing into a kernel smoother. And this is just the typical Nadaraya-Watson kernel smoother. And all what you need to specify for this is some kernel function, which for us is a smooth symmetric density with finite support. And then you need to specify a bandwidth, which controls how much of the data is used to estimate at each point, essentially. And we give a rate at which you should specify it between n to the minus quarter and n to the minus half. And this is sort of standard kernel smoothing stuff. So just to recap, the process for getting the final estimator is first to fit the regression model on the treated individuals. Then we perform smoothing on the predicted values using the smoothing estimator I just showed you on the last slide. And then we apply that to the control arm. We plug it in this sum. Everybody here is in the control arm. So this SI is for everybody in the control arm, but we're sort of plugging in their mean function from the treated arm. And that gives us this residual treatment effect. And then we can plug that into the PTE, and we're done. Okay, so that was the first approach. The second approach is a kernel-only approach. And recall that I said that we would like to use kernel smoothing, but we can't because of the cursive dimensionality, because S is p-dimensional. It turns out that the cursive dimensionality can sort of be sidestepped by exploiting the topology of functional or longitudinal data. And what I mean by that, there's this cool paper by Guinans in 2011, which goes into great detail about this idea. But on a sort of basic level, it turns out that a lot of functions or longitudinal trajectories, like we're interested here, actually live in pretty low dimensional spaces. So these are the top three eigenfunctions that we estimated from the longitudinal data that we actually analyzed in our paper. And these eigenfunctions are sort of like the principal components of the function space. And so these three functions explain most of the variability in the data that we were using from this AIDS clinical trial. And in my practical experience, typically when you try to estimate these functions, which explain most of the variability in your data, there are typically only just a handful. And so here you get something that's sort of like a mean over time, and then and then a couple of functions that introduce some curvature. And when you use those things, it actually turns out you can do a pretty good job of recreating the longitudinal trajectories that you actually observe. So again, this is from the data that we analyzed in the paper. The blue dots are the observed CD4 counts over time for a bunch of people in this clinical trial. And these red curves are what we estimate using just a few eigenfunctions. So basically doing dimension reduction into a small number of functions and then trying to recreate people's trajectories, you can actually do quite a good job. All of which is to say that really you're not dealing with a p-dimensional space. You can really think of this as a much lower dimensional space. So using that idea, you can define a distance function that determines how far away two surrogate trajectories are from each other, that is sort of less hamstrung by the cursive dimensionality. And the thing that the sort of technical name for this thing is a semi-metric. And a semi-metric is sort of just like a typical distance function that you're probably used to, in that it's symmetric and the distance from one function to itself is 0 and it obeys the triangle inequality, but it has this feature where two functions that have a distance from each other of 0 don't necessarily have to be the same. So what that means is that as long as they have like, if they're the same in these dimensions, if they're the same in the dimensions that are defined by these eigenfunctions, then as far as this new distance function is concerned, they're the same. So it allows you to focus in on, again, this sort of much lower dimensional subspace of the functional space. And this is what this thing looks like. Basically, you take the distance, the difference between the two functions that you want to get the distance of, and you project that into the eigenfunction space, and then you sum over the eigenfunctions. So this may not all be crystal clear if this is your first time seeing it, but the main idea, again, is just that we get to live in a much lower dimensional space. So that semi-metric allows us to use a traditional kernel smoother. So that the semi-metric in this version is the dimension reduction step. So once we have that distance function set up, we can just plug it in to a traditional Nadaraya-Watson kernel smoother. And again, we have a bunch of technical conditions on what the kernel function needs to look like. It needs to be bounded in Lipschitz, and we have some rules for what the bandwidth has to look like. And here the bandwidth now depends on the number of eigenfunctions that you include in your metric up here. So the final version of this estimator is we choose the semi-metric, and in large part that means just choosing the number of eigenfunctions or dimensions that you want to live in to capture the space of functions. And then you can compute the kernel smoother in the treatment arm, and then you apply it to the control arm and then compute the PTE. There's also a convenient implementation of this kernel estimator in the FDA.usc package. And our work builds on what they've done. Okay, so those are the big ideas that we have, this two-stage approach that we hope is pretty non-parametric. And we proved some stuff about how it behaves. Regardless of which of those approaches you use, we get limiting normal distribution at a parametric root and rate. So despite the fact that we're using kernel smoothing, we get this nice parametric rate. The drawback is that this thing that it's converging to is not necessarily the true R. And it really depends on the adequacy of the dimension reduction step. So this thing that it's converging to is going to still be dependent on the initial regression model that you fit, or the semi-metric that you choose for your distance function. So we're not entirely non-parametric. We can't guarantee that you're going to get the right thing. You're still going to have to do a good job in that first dimension reduction step. And the other thing to mention is that for the kernel-only regression estimator that I mentioned, the last one, this result requires that you only include 2 eigenfunctions in the distance function, which probably isn't going to be realistic in practice. This probably isn't enough. So, there are some other restrictive technical conditions in our proof, which probably aren't going to be met in practice. But despite all that, when we use it in simulations and violate these technical conditions, it still seems to work out fine. We also give expressions for this asymptotic variance, this sigma squared here for all the estimators. But it's not very beautiful. And there are things in there that you probably wouldn't want to have to estimate in real life. And our simulations also suggest that in finite samples, the PTE may typically have a skewed distribution. It's a ratio of two things that are both converging to normals. So in many finite sample situations, it's probably not going to have a distribution that's well approximated by the asymptotic result. So we recommend and implement in our package to just use the bootstrap for estimating the variances. Okay, wrapping up this bit, maybe a little bit ahead of schedule from what I had done. We propose two-stage kernel smoothing estimators to evaluate the utility of longitudinal surrogate markers. We take advantage of the unique topology of functional and longitudinal data, either through state-of-the-art functional regression methods or through this sort of sidestepping of the curse of dimensionality through the use of eigenfunctions. There are a bunch of additional bits in the paper that you may be interested in, including, like I said, how to deal with situations where you have sparse longitudinal data, where if your surrogates are measured at irregular time points and a different number of observations for each individual, we talk about how to deal with that. And our simulation suggests that all these methods should still work quite well in that setting. We have a bunch of simulation results, including, different data generating mechanisms and which of these estimators seems to work best in which types. And we have an application to an AIDS clinical trial data set where we're looking at which, whether CD4 count as measured in the first year after treatment initiation can be a surrogate marker for long-term CD4 count. And please check out the paper and our package, which is called LongSur, and it's available on GitHub, and would love to hear your thoughts about it if you're interested. Okay, so now I'll spend a little bit of time talking about this recent extension of this work to high dimensional data. Are there any questions before I move on to this piece?
I had thank you very much. That's very, very, very clear and very interesting. I had some question about the nature of why. I missed maybe this information. What kind of outcome do you deal with?
It shouldn't, just as long as it's fully observed, like not time to event, it should be okay. So I think probably these functional regression methods are set up, and what we looked at primarily in the paper are continuous outcomes. I think that probably would work fine if you had a binary outcome, either by changing the regression method to be more like logistic regression, or by the smoothing step. Even if you fit this penalized linear regression on a binary outcome, I think that the second stage of smoothing might recover the true mean function, even if the first model is relatively misspecified.
And could you deal with repeated Y also? Oh. for the moment, this is not what you do.
Yeah, it's not, it would be more difficult to define what the overall treatment effect is. So we haven't thought about that yet.
Okay.
But yeah, I would love to talk more about that if you had an example.
No, but I was thinking, yeah, of a clinical, for example, a clinical outcome that would be repeated, and your surrogate would be maybe the biology or something like that. And I was thinking about, yeah, but maybe you can take what you take is the level of the clinical marker at a certain time, and that's your outcome.
Yeah, and I think you could probably define this quantity for at each time point that you have the outcome at, and you may get a higher proportion of treatment effect explained at different time points of the outcome.
And if I may also, what would be the difficulty to work with time to event Y?
We'd have to, I think for the kernel-only approach, I don't think there is any difficulty. I think you could define, there are well-defined kernel style estimators for time to event outcomes. So if you do the kernel-only approach, this one, then you just change these things appropriately. You just have some kernel function in here that this could be transported into whatever your favorite time to event kernel estimator is. For the functional regression methods, I'm not sure if those methods are well developed for time to event outcomes. So, but I think for this approach, it would work well.
Okay, thank you. I let you finish. Thank you.
Okay, so some compromises that as we continue to work and think about these issues that we had to make for that previous paper that I talked about, I'll run through some of the compromises that we had to make. So first, we assumed the treatment was completely randomized. And obviously in some cases, that's not going to be the case. And as I'll argue in a moment, a lot of times these surrogates may be of interest in observational studies. We were really at the mercy of the dimension reduction, like I mentioned in the asymptotic results section. If we don't get the initial stage right, if we don't specify the distance function correctly, or if we don't specify the initial regression model correctly, then we don't have any guarantees of how close we're going to get to the true value. Our theoretical results ignored model selection. So when we actually applied these methods in our paper to the AIDS clinical trial data set, we have 3 different ways you could analyze it, 3 different potential estimators. And so we did some sort of cross-validation approach to choose which one seemed to be the best fit to the data, and then we went with that one. But obviously, we don't have any theoretical results for what would happen if you actually implemented such a cross-validation procedure in practice. We only considered, we have three different methods, but these are a relatively small class of models, considering all the models that are out there to estimate regression functions and do prediction. And we really are relying heavily on being able to understand the asymptotic behavior of these models. So using something like random forest or deep learning or whatever isn't on the table because of our analysis techniques. But also, what if I just don't care about longitudinal data, but I have some other high dimensional set of observations that I'd like to use as a surrogate? So I could have a p-dimensional set of gene expression measurements that I'd rather use. You'd think that these would be similar similar strategies could be used. And I think that this topic is actually much more prevalent than maybe it's been realized. There's this paper that came out just a couple of weeks ago where they talk about post-prediction inference, and they say that this is happening all over science, where people have some machine learning algorithm that gives them a predicted outcome, and then they use that predicted outcome in downstream analyses. That is exactly surrogate outcome research, and people are doing this all over the place and without thinking about it or having any well-developed methods around it. And so I think that like having very general non-parametric methods for evaluating these types of things is super necessary. And so what we've proposed is a method for estimating the PTE, like I defined earlier, for basically any surrogate. It could be high dimensional or low dimensional. It could be a longitudinal. It could be a mixture of different types. It could be an observational data, and you can use any estimation method you'd like, including machine learning methods or high dimensional regression methods, or an ensemble of any of the same. So just to give you a really brief flavor of what this is, recall that this is the thing that we're trying to estimate. And it involves these two things that are average treatment effects. So this delta is the overall average treatment effect, and the residual treatment effect is basically the same thing, but just conditioning on the surrogates. And there are really well-developed ways to estimate average treatment effects in the causal inference literature. So under very typical assumptions here, now I'm assuming that we're in an observational setting where we have covariates X that you need to control for confounding of the treatment assignment with the counterfactual outcomes. People have proposed doubly robust approaches to estimating these treatment effects, which have nice properties like attaining the semi-parametric efficiency bound and stuff like that. And this is what the doubly robust estimator looks like for the residual treatment effect. And again, if this is your first time seeing it, this is probably pretty ugly. But the main thing to notice is that this thing just depends on the observed data, the A's and the Y's, and then a few unknown functions. And the unknown functions are this pi, which is the probability of treatment given the covariates and the surrogate, and this is akin to a propensity score. And these mean functions, and this is the type of thing that we've spent this whole time talking about, how to estimate. And the overall treatment effect has a similar expression where all this stuff just doesn't include S. And it turns out that you can, that people, Viktor Chernozhukov and his group have shown how you can use machine learning to basically estimate all that stuff. And when you use sample splitting to do that, you can use essentially anything you want. We, in our paper, use an ensemble of different estimators, which we combined via the superlearner. And we also have a version of it where we just use the lasso. And when you do this, even when you use this like ensemble method that is very difficult to understand its asymptotic properties, because you do sample splitting, the asymptotics of the estimator of the PTE are really simple, and variance estimation is really straightforward. And these are some simulation results. I maybe am just going to skip this, though we can come back to it if you'd like. But I do encourage you to check out the paper. I just put it on archive yesterday. I think it should be in the archive email this morning. And we'd really love comments on it if you have them. And I really appreciate your attention, and I thank you again for the invitation to come talk to you guys.
Okay, thank you, Denis. Are there any questions?
Yes, I have a small question.
Go ahead.
Thank you for the presentation. It was very interesting. I have a question mainly about the first part of your talk. You propose a method that is specially designed for the situation where you have a lot of time of measurement for the surrogate. In case where your longitudinal surrogate is sparse measures, as it is the case in most applications, I think. Did you compare with multivariate modeling of the outcome and the surrogate using a flexible approach with a spline for the evolution of the surrogate and the spline for the link function for the association between both? Did you try that?
We didn't try that, but would be happy to talk to you more about trying it and seeing when it would. You have your thought is that it would be better when you have just a few time points.
Maybe in any case, I'd like to know if you have a clear superiority of your approach in this case.
No, definitely not. And I think we know that from our simulations that when the time points are very small, then our method does degrade in performance. So I do think that there's probably some headway there to be made in trying other methods for sure.
Okay.
QLN, other questions?
So to continue with this question, what would be your recommendation? What would be the minimum number of repetitions we should have?
It's hard to say, I think.
But from your simulations, maybe?
Yeah, so from our simulations, we started out with a large number of time points and then sort of randomly selected time points from within. So in that case, the sort of denser you get the grid of time points, then the better their performance was. And I think it was sort of between 5 and 10 per individual in our simulations. But if you have but I do think that it probably just really depends on the underlying data generating mechanism and how closely aligned, like how dense the measurements are in the possible time grid. That it's difficult to say, I guess.
Okay, that would need simulations in the application context that we could think of.
What's that?
We would have to redo the simulations with parameters mimicking our applications to be able to understand that.
Yeah, I think so.
Mm-hmm.
And I think that our particular approach, which when we had only a few measurements per individual, we did this thing where we tried to fill in the entire grid using the approach I showed you with the eigenfunctions, and then using regression models on the entire grid. But I do think there are probably a lot of other ways to fit an initial regression model that does a good job and doesn't follow the path that we did, but then you could still use the sort of secondary smoothing approach that we used to sort of save yourself from any model misspecification. And I just think there's sort of a lot of flexibility on that first stage that you could explore for sure.
And so probably also to deal with measurements that are not at the same times for all the individuals, probably by just changing this first step. Right. Yeah. And so, yeah, like I said, we chose to try to like fill in the entire grid using this principal analysis via conditional expectation method, but in another situation, you might have better luck doing something that's more customized to your actual scenario.
Okay, thank you, Cécile. Are there other questions? So if not, I do have a few questions, or at least clarifications that I wanted to ask. So I really like your simple example at the beginning. I think it's very clear to understand what you're doing, but I just want to clarify something, because when we see this example, you show that basically we can have a widely misspecified model for the dimension reduction part. And thanks to the later smoothing, you're able to recover a good prediction, good estimation. But then you in the discussion, you spend a lot of time saying that basically you're at the mercy of how good you're doing with this dimension reduction step. So again, if we go back to the first example of S1 square and S2 plus S2 square, would, for instance, if let's say you don't have S2 at all in your model, would that then like really hurt the method, and you wouldn't be able to recover the curvature, for instance, that was just shown in the previous graph, I'd say?
Yeah, I think that's a really good example. I think you would still get some of the curvature, you know, but
Yeah,
I think
S1.
you'd get less. Yeah, exactly. And so I think that that's maybe making the point more succinctly than I could have, which is that, or than I did, which is just that the smoothing step will definitely get you closer, but it's hard to say how close, you know, and it really depends on the strength of that initial model. And we think that in general, it's probably going to be pretty close, but we don't have any guarantees.
And then, so you mentioned in the end that in some finite sample setting, you recommend to use a bootstrap. I was just wondering how much of a computational burden that is for your approach.
It ended up being it's not that bad. Like the stuff that I talked about here is not super computationally burdensome. I mean, mostly it's penalized linear regression and kernel smoothing, neither of which is very difficult computationally. If you do the secondary or the sort of like pre-processing step that we actually have spent a lot of time talking about here in the post discussion about trying to fill in the grid of points and estimating the underlying trajectories for each individual, because you only have a few observations per individual, that takes a long time. And when you have to bootstrap that thing, then the process is much slower. But if you have if you don't have to do that sort of initial imputation step, it's quite fast.
Okay, and so well, if anyone else has some questions, feel free to interrupt me. Otherwise, I'll continue with my list. Okay, so you mentioned that you're not able to use a random forest, and it's just not super clear why.
Well, we just wouldn't be able to get any asymptotic result. But so you of course could.
Since in the end you rely on the bootstrap, would you be able to do that with the bootstrap?
I suspect, yeah. And so yeah, I think that there is a disconnect, though. I guess I prefer to have some asymptotic result, some sort of guidepost to tell me that the thing that I'm doing is going to give me a reasonable parametric rate of convergence, and I just wouldn't have that with, at least I'm not aware of how to obtain something like that with in a general way with using random forest or something like that. I do suspect it would probably work fine, but it just with fewer guarantees on convergence, I would say.
And maybe, so one last question for me is, again, you said that for your asymptotics, you need the bandwidth to be in the order of n square or n to the power of half or anyway, the usual non-parametric rate. But so in practice, what do you use for the bandwidth specification?
We use like, I think it's like the standard deviation of the x-axis times n to the minus whatever.
Okay.
I forget now. This, but I think, yeah, I think it's just like some n to the minus in that band times the standard deviation of the x value.
Okay. Because in my experience, when you said that the kernel smoothing was quite fast, it can take some time to cross-validate when you do also bandwidth estimation. But if you're using something straightforward, then that's.
I do think we used like an actual pre-specified value.
Yeah, I mean adapted to your number of observation and I mean to your data, but that's.
Yeah.
Okay, cool. I don't have any other question. We still have 2 minutes if someone has something else they would like to ask. Well, if not, we can thank Denis again